Uh, Now we see a flow chart of the genetic algorithms that you see we start from the solution means a population of designs. Okay, initial design usually created by uh, random numbers. Okay, uh, have a number of chromosomes. Then we need to, based on how good they are, then conduct a selection. Uh, I don't know the sequence of what is that. Crossover, just like what we had said that they will swap, or the children will get some gene from father, some get it from mother. Mutation, small bit, change, swap. Then we need to do evaluation. Okay. Then based on the finish, we do the selection. And this is there are a lot of ways to do that, but this is one way to do that. Okay, that's the end of this file. And I will using another file, provide more content. Okay, you are seeing that another node. This one was created in Israel, okay, another university, and I thought that the node is quite good, provide some new information. So I want to use that to give you some more idea. Okay, some are similar, but some have new idea. Okay, genetic algorithms is class of probabilistic optimization algorithms because we have random numbers. Okay, random number will determine by in the ruler wheel, right? We spin the ruler wheel using the random number to decide which one should be in the next generation. So it's probability based. So a good one not necessarily will be selected. A bad one sometimes can be selected. Okay, so that's called a probability. And also which one to do the crossover based on the probability. Okay, mutation, which bit will conduct in the mutation is a probability. So every time you start from even with the same population initial design, the genetic algorithm outcome will be different because the random number might be different, will be different. And this is inspired by the biological evolution process, using the concept of natural selection and the genetic inheritance. Okay. And the genetic algorithm was first developed by the professor in Michigan University, okay, John Holland in 1975. And genetic algorithm can be considered as the most powerful optimization problem so far. So it's particularly well suited for hard problems where little is known about the underlying search space. It means that even the design optimization space is very complicated, and who cares? Okay, genetic algorithm don't care about that one, and widely used in everywhere. This is a position of the genetic algorithm search methods and guided random search methods because we're using some random numbers. So it's belong to the category of guided random search. And random search has different approach. We belong to evolutionary algorithm, okay, than genetic algorithms. Genetic algorithm maintains a population of candidate solutions for the problem at hand. and make it evolve by iteratively applying a set of stochastic operator. Means that we evolve one generation to another generation, then we evolve that generation from a further next generation. Every generation we iteratively means that we do the same thing, 3 operations. One is a selection, crossover, mutation. Okay, and those are all stochastic operators. Stochastic means probabilistic, same, something related to the chance. Okay, it's not heuristic. So selection, recombination is crossover or mutation. Every operation we have to use in a random number. So it is stochastic. The metaphor is how this in the nature and how it is in our genetic algorithms. Okay. In optimization, genetic algorithm is solve optimization problem. Okay. In the nature environment. Okay. Environment we live. Okay. And here we talk about feasible solutions. In nature, the individuals living in the environment, like a human or flower or orchid or tiger or elephant. Okay, those are those are solutions here. And in our genetic algorithm, we are based on fitness function to determine how good a solution quality. In nature, individuals' degree of adaptation to its surrounding environment. Okay? Like if you are a fish, how fast you can swim. Okay, if you are lion, how faster or how flexible your movement. And when you are hunting, you need to be faster. Also, you need a very flexible body. And for a male lion, you need to be strong, a big mouth, a big force to fight with another male lion, right? Those are necessary property required for adaptation to its environment. And a set of the feasible solution in nature is a population of organisms or species, like a lot of human, a lot of rabbit. In nature, never says only one lion, right? Only one human. No, we have 6 billion human. We have a lot of cockroaches. We have countless the cockroach. We have many fishes. Okay, so population. In genetic algorithm, we have stochastic operators. We have a selection, crossover, mutation based on random number. And in nature, they have a selection, and recombination, and a mutation in nature's evolution process. Okay, in nature, the selection were based on if you are good, you got a chance to get married, and you give more children, and something like that. And literally applying a set of stochastic operations on a set of feasible solutions. In nature, the evolution of populations to suit their environment. The computer model introduced simplifications, means that we cannot run exactly the same evolution like in the nature. We simplify them, okay? But still, surprisingly, we still provide a complex, interesting structures and can be applied effectively to a lot of evolution in algorithms. This is the algorithm. I think that we all know that now. That's also the flow chart that we know. Okay, first selection, select the new parents. Okay, then we do the crossover mutation to change new offsprings. Then we do the evaluation. Then we have new population. Okay, there's a new example called a max1 problem. Suppose we want to maximize the number of ones in a string of L binary digit. For example, that we have 20 binary strings. They are all 0 or 1, right? But we want everyone to be 1. Just like that to be or not to be problem. Okay, we know the final automatic design is everyone should be 1. How to run this starting from arbitrary binary string that will automatically evolve into everyone is 1, okay? So an individual is encoded as the string of L binary strings. Then finish of a candidate solution to the maximum 1 problem is number of ones in its genetic code. Like if you have 20 bit, then right now in the 20 bit, you have 6 1, you have 12 0. So finish with only 6. Okay. Then we start with a population of n random strings. Suppose that L is 10. So we have 6 designs. Everyone have 10 binary strings. Like that one. We toss a fair coin 60 times. Actually, we're using random number to determine 1 or 0. If random number is smaller than 0.5, we set it 0. Larger than 0.5, we set it as 1. So we get random number 60 times, we get a 60, 0, 1. So they form 6 binary strings. And then we see that the first string has 7 ones, so it's a finish 7. So this is that one. So average will be 6, something like that. And then based on this finish, we will provide the ruler wheel, right? For example, the first one, 7 divided by, I don't know, total 11, 15, 20, 34. Total 34. 7 divided by 34 will be like 20%. And this one only 10%. Okay, so everyone have a share of area, and they shoot 6 times. So the new population. After you shoot on the ruler wheel six times, then you got new parents. Then you do crossover. Then you do mutation. If, for example, that they do before crossover, but after crossover they exchange the final part. And these two exchange from 6 to 10. Okay, then become that one. Then do some mutation. The red one means that one will be conducted mutation. So after that one, in one generation, the total population finished changed from 32 to 37, improved a little bit. Okay. After selection, crossover, mutation, they improve a little bit, but they continue to do that. As we went through the same process over again until stopping correlation. So you can expect that if you run a few generations, everyone will become 1. Components of a GA. Encoding principle, gene, chromosome, initialization, creation, selection, parents, reproduction. Possible individuals encoding, okay. We teach binary strings, okay, 0, 1, 0, 1, but there are some other different schemes. We are not going to go through with them. And this is how you should read or pay attention when you choose an unencoding method. You really know these kind of ideas. That's what I said. The better one is you create a binary string one-to-one matching. Okay. And I don't want to go through this because we already taught that one. But there's a good example I want to discuss with you. Okay, this one. This one is very famous optimization problem called the traveling salesman problem, TSP. Traveling salesman problem, TSP. It means that, of course, if I want to send you to visit a customer, okay, but the customer, the location of customers, company located in different city. If you work in USA or in China, that big country, for example, that you are in Shanghai, then you have 150 customers, and they are spread located in maybe 74 different cities inside China. And they want you to determine a sequence. Which one to be busy first, which one to be busy second, which one to be busy third, which one to be fourth, by that. So you have 100 customers. So you need to determine a sequence to contain the 100 customers. So the sequence can be 1, 2, 3, 4, 5, all the way to 100. But you also can 1, 3, 17, another sequence, right? Wow, the sequence, the possibility of the sequence is large. So there are way too many large number of possible sequence. Which one is best? It can be decided by the distance, okay? For example, if you drive your car, then you determine a sequence and to visit 100 customers by driving the total smallest kilometers distance, so that you can save a lot of gasoline money, right? That's one way to determine the fitness. What is the short is the distance. The second way is smallest budget, traveling budget. For example, that in USA or in China, that spread in 45 cities, you will not drive all the way to there, take too much time. Sometimes you have to fly. You fly from Shanghai to Chengdu, from Chengdu to Sichuan, to Chongqing, from Chongqing to Guangzhou, from Guangzhou to somewhere. A lot of traveling, fly. And you will know that, especially that like in USA, the traveling airfare, the ticket for the air flight from one city to another one is not depending on the total distance. It depends on the supply and the demand. For example, that from New York City to Boston, sometimes it's 200 US dollars, sometimes it's 500 US dollars, sometimes it's 50 US dollars. Depends on how many wants to fly, right? If no one wants to fly, they have to reduce the airfare so that people will take it because it's cheap. But if everyone want to fly from US, from the, for example, from New York City to Los Angeles, everyone want to fly before the Christmas, then the airfare will be 3 times, 4 times more expensive. So when you determine how to visit 100 customers, you have to make a better the itinerary, so that the budget you pay for the flight to cover all these kind of visit will be smallest. So it's very complicated. And it's very difficult to run by traditional optimization problems. So let's see how we run this traveling salesman problem. Because this is important, pay attention, because it is one of the two project problems I offer to you. One is to run the traveling salesman problem. The other one is to run the trust optimization problem. Okay, I'll define it next week. Okay, so for example, here is how should he plan his itinerary for minimum total cost of the entire tour. TSP is a non-MP complete problem. Okay, you can check out by yourself what is an MP complete problem. Okay, first we need to create a representation scheme. Okay, for example, if we have a 10 customer to visit, so we need to see 1, 2, 3, 4, 5, and 10 in the sequence, right? So we need to create a vector. In a vector, we need to have 10 numbers. Okay, the 10 numbers, each one represent the customer number. And so in every vector, need to have 10 numbers, 10 different numbers. You can have a 2, 1, or 3, 2. Every number can have only happen once in the vector, okay? But the sequence can be different. And fairness of a solution is the inverse cost of the corresponding tool. The cost is the smaller the better, but fairness is the higher the better, right? So we do the inverse cost. For example, but we can 1 divided by cost, okay, something like that. And initialization, we're using some heuristic or a random sample of permutations. For example, that we're using random number. Okay, for example, that let me show you by using whiteboard to give you one example how to do that. For example, that we have 5 cities. Make it easier, we only have 5 here. 1, 2, 3, 4, 5, right? And we need to find out 1, 2, 3, 4, 5. And how about make it 8? Make it 4. 4 is easier because the only 4, we need only 2 bit, right? 0, 0, 0, 1, 1, 0, and a 1, 1. 4 bit. This one represents the first one, 1. This one represents 2. This one represents 3. This one represents 4. So we need to have a first 2 bit created by random number. So it could be 0, 0, it could be 0, 1, it could be 1, 0. Because first one don't have restriction. First 2 bit. And after that, if first 2 bit is 0, 0, means that 1 is already selected, right? 1 is already selected. 1 is already selected. This one means that 2 already selected. This one means 3 selected. This one, 4 selected. Then in next 2 bit, you cannot have the 0, 0 again, right? So you're using random number to generate the next 2. If 0, 0, then you cancel that. Just don't accept it because you already have 0, 0. Right? So things that 0, 0, you don't accept it. So only these 3, you can accept it, right? Only when 0, 1, or 1, 0, or 1, 1, you can accept it. If 0, 1 means that 2 are selected, 1, 2. If 1, 0 means a 3, so you are already at 1, 3. If 1 1 means then you have 1 4. So if 0 0 1 1 is the case, 1 and 4 was selected. So the next two customers can be only 2 and 3, right? So you let a random number to generate only when 2 or 3 happens, then you accept it. So the next one, if it's 01, means 2. It's okay, then you will have 1 4 2. Then last one, you don't need to random number because the last one should be 3, so it will be 1 0. So that's why you can create a binary string, contain a binary string. Okay, you have a bit, 2-bit here, 2-bit here, 2-bit here, 2-bit here, 2-bit. You create a bit, and first 2-bit represent the first customer, either 1 2 3 4, and then either 1 2 3 4, either 1 2 3 4, either one. But only happen once, one customer. And that's called you need some rule.
30 seconds until minions spawn.
But this is only one way. There are a lot of ways to do that. I only provide one example how to do that. Okay. We need to do initialization using some heuristic or commutation. Okay, then once you have, now we discuss selection
Minions
later.
have spawned.
We decide how to do crossover. Okay, crossover takes time. I will give you an example again by using whiteboard because it's difficult to see here.